All right. The conversion between PSI to pounds per square foot is just you multiply by 144 to get PSF. So if you have 1 pound per square inch, it's 12 by 12 inches on a square foot. And so if you have 1 pound on each of the inches, then that would mean on a square foot there's 144 pounds. So just a reminder about that conversion. The continuity equation, which I'm sure you learned last semester, is that flow rate is velocity times area. So there's one of the problems where the units are traditional units, and I believe that in that problem you're given the flow rate in cubic feet per second and the channel geometry from which you can calculate the cross-sectional area. And so then the only thing that would be unknown in the continuity equation with a problem like that is the velocity. So the units here is that if you're solving for velocity and you know the area and the flow rate, then you just would divide the flow rate by the area, and from that you can get the velocity. And then one more hint as I was looking through the assignment of things I wanted to just reiterate and point out is in a piezometer, the difference in water elevation between an upstream and a downstream tap, so this difference in measured water elevation, that is H sub F. That's the head loss due to pipe friction. If water was flowing through a frictionless pipe and there was no resistance to flow, then the water level would rise to the same height. But it doesn't, and the decrease in elevation downstream is H sub F, the head loss due to pipe friction. So you've got one of the problems with the figure very similar to this, except for that I think the H sub F is quantified. And I wanted to point out that this deflection between the upstream and the downstream head is because of pipe friction. All right, so go ahead.
I have a question about one of the homework problems.
If we have time at the end of the class, then we can go over it, but we actually do have quite a lot of other things that we're going to cover today, and it may be something that is in the lecture would address that.
Right.
So if it's a homework problem question, then let's just defer for now. So the last couple of lectures we were in the first part of chapter 7. We're continuing on through the velocity distribution stuff that's up until section 5 of chapter 7 today. And one of the slides that we didn't get to last time was talking about shear velocity. And so shear velocity is a way to transform shear stress. Shear stress has units of newtons per meter squared. Let the ambulance go by. So if you combine the definition of head loss due to pipe friction and the relationship between shear stress and head loss, both of these were introduced in previous classes. If we combine it together and cancel out like units, then what we'll end up with is this equation on the right, which relates the shear stress and the Darcy-Weisbach friction factor F. Now, if we further break that down and look at the units of it, what we're going to see is that there's this factor that has units of meter squared per second squared. And so if you look at the left-hand side of this dimensionally homogeneous equation, and dimensionally homogeneous means that the left-hand side of the equation has the same units as the right-hand side of the equation. And oftentimes an empirical equation, which is just curve fit and not fundamental in nature, will not be dimensionally homogeneous. But when you're working with fundamental equations, they often are. And this one is dimensionally homogeneous. So we just have to look at, for example, the left-hand side of the formula to know what the units are. So for that, we've got the shear stress divided by density. Now shear stress has units of newtons per meter squared. That's this first term here. And then density is kilograms per cubic meter. And so the inverse of that, since it's in the denominator, is kilograms down below, cubic meters up on the top. Now, newtons can be broken down further because all units are derived from either mass, length, or time. And so newtons, for example, is a unit of force, but it's just a combination of mass, length, and time. And so if we break newtons down further, a newton is a kilogram meter per second squared. And so here, kg times meter divided by second squared. is the newtons being expanded out with its units. This meter squared is still in the denominator, and then the units of density, where it was meters cubed in the numerator and kilograms in the denominator, this is the entirety of the expression, which we cancel out, for example, the kilograms in the numerator and denominator. We've got meters to the fourth in the numerator, meters to the second in the denominator, and so cancel that out. And what we're ending up with is meters squared per second squared. So the reason why they thought of this as a velocity is because if you take the square root of both of these, then what's left is just meters per second. So it's kind of a transformation where we could think about shear stress with these units of velocity, and this shear velocity, V star, is just the square root of the shear stress divided by the fluid's density. So you've got, I think, one or two problems where the shear velocity comes into play, and this is the formula that you should use for calculating that shear velocity. And we can further relate it to the Darcy-Weisbach friction factor with this formula that's in the box. So if you know, for example, the flow conditions, and you use the Moody diagram to find F, and you know the flow velocity of the water, then you could, from those two things, calculate the shear velocity, which is related to shear stress. Shear stress is really difficult to measure directly, but friction factor is easy to estimate, and velocity is easy to measure. And so shear stress becomes a little bit easier to understand with this notion of shear velocity. The other slide that we didn't get to in class on Wednesday was thinking about shear stress in open channels. This is a trapezoidal channel, and we'll see a lot of trapezoidal channels this semester, where we've got some side slopes leading to a channel bottom that has a width of B. And the reason why it's typical to have trapezoidal channel geometry is grass line channels or earth line channels couldn't have a vertical side slope. We can make a vertical side slope with concrete or rock, but other materials don't have the strength to hold up when water is flowing through a channel. Like a vertical sidewall like that would just collapse if it was soil. The shear stress that's being applied by the water as it's flowing would just eat away at it until it finds some stable equilibrium having to do with the angle of repose. But the side slopes like this makes it so you can have an earth-line channel. And the way that we describe how steep the side slopes are is there'd be some ratio of the vertical to horizontal distance. And the formulas that we use assume that we'll have 1 unit of vertical to t units of horizontal. So if t was 2, what that means is for every unit of depth, you'd have 2 units of length on the side slope if t equals 2. Or if t was 1, then it would be a 1-to-1 side slope where each unit of depth, y, gives you an extra length across the top. So this top width, capital B, is longer than the bottom width, lowercase b, because of the extra distance applied by the side slopes here. Now we can apply the definition of shear stress also to a trapezoidal channel. Remember, the definition of hydraulic radius, R, is it's the area divided by the wetted perimeter. In a pipe, the wetted perimeter was, if the pipe is full, it's the entire circumference of the pipe, because water is touching material the entire distance. But in a trapezoidal channel, the wetted perimeter is a little bit different. The wetted perimeter is only where the water is in contact. So it would be the sides and the bottom, but not the top. The top is not included in the wetted perimeter because water is in contact with air, which provides only just a little bit of resistance, much less than the resistance that's applied to the fluid by the channel itself. So wetted perimeter only includes the side slopes and the bottom. So S sub F, remember, is the slope of the energy grade line. And when we've got open channel flow that's steady and uniform, then the slope of the bottom of the channel is the same as the slope of the energy grade line. So in steady, uniform flow, S sub F equals S naught, the channel slope. Okay, now, what is the hydraulic radius for a trapezoidal channel in terms of B, Y, and T? The geometry of a trapezoidal channel is going to be really important this semester. Some of the formulas that we'll use are pretty easy for a pipe, but then they get complicated when we apply it to a trapezoidal channel. So this is just a first taste of the geometric parameters that are applied to a trapezoidal channel. And so let's say that we have, let me just move this up here. Okay, we've got a trapezoidal channel, and the side slopes are defined by 1 is the vertical component and T is the horizontal component of the side slope. Okay, so it has some depth Y. Y is the depth of the water, and we're going to want to know the area and the wetted perimeter. Okay, so the area, you can see that there's basically here, there's one rectangle which is the main body of the channel here, and then there's a pair of side triangles, which if we put these two triangles together, it's another rectangle. So let's say that the area is B times Y, and that's this first rectangle because the bottom width is the base of that, and Y is the depth of the flow. So area is B times Y plus Y times T times Y. And that is Y here, and then Ty is this distance. Because if, for example, it's a 1-to-1 side slope, then for every unit of depth we've got, then there's also going to be the same distance across the top. Now the wetted perimeter is going to be this distance, the bottom, and then the other side slope as well. Okay, so this distance is y squared plus ty squared, and then we take the square root of that because there's a height and a length, and so the wetted perimeter is going to be the bottom width b plus 2 times the square root of y squared plus ty squared. And we can further reduce that so that the perimeter is the bottom width plus 2y times the square root of 1 plus t squared. So then the hydraulic radius is area divided by wetted perimeter. So R is A divided by P. So that is by plus T times y squared divided by B plus 2y square root of 1 plus T squared. Okay, so this is just, like I said before, an early taste of trapezoidal channel geometry. You're going to have to calculate the hydraulic radius when you use Manning's equation. Manning's equation is one of the formulas that relates resistance to flow and flow rate. And it requires you to have the geometry of the channel defined. And so if so many of our open channels are trapezoidal, you'll get very good at substituting in the trapezoidal geometry into Manning's equation. All right. Now, another one of the flow resistance equations, an empirical equation that was developed years and years ago, was the Chezy equation. And what Chezy observed was that there was a relationship between the velocity of flow through a conduit and the square root of the energy grade line and the hydraulic radius. So you do have a problem in the homework where I'm asking you to use the Chezy equation, and the way it works with the Chezy equation is that a low C value is going to give you a low velocity. And so a rough pipe would have a low C value, and a smooth pipe would have a high C value, which would allow the formula to give you a velocity that's higher in magnitude for a certain slope of the energy grade line and a certain channel geometry that is defined by the hydraulic radius. The Manning's equation, which I mentioned a few moments ago, improved on the Chezy equation because it found that the flow conditions were actually related to the hydraulic radius to the 2/3 power rather than to the 1/2 power. This is just a best fit approximation relating resistance and flow rate. And so when you've got more data and you've run more experiments to try and find that best fit, which is what Manning did, then the formula can change a little bit. But it's still useful to know a little bit about the Chezy equation because so many things were designed long, long ago. So you may end up someday rehabilitating a pipeline or a canal that was designed with the Chezy equation, and you'll need to understand what were those design equations and what were the assumptions and what were the formulas that were utilized. And so we can convert between a Chezy roughness factor C and the friction factor that goes into the Darcy-Weisbach equation with this conversion. This comes from page 201 in the book, just relating roughly the friction factors on the Chezy scale to the friction factors that you'd get if you used the Moody diagram. We don't do lots of history in engineering, but a lot of hydraulic systems were built a long time ago, and so sometimes a little bit of history is important. All right, when water's flowing through a conduit, the water, let's just say water in the middle of a pipe, which is further away from the edges, is going to have a larger velocity because of the no-slip condition. So remember, it is that stationary pipe applying a shear stress to the water that is resisting flow. And so the further away you get from the edge of the pipe, the water is able to flow more freely. So in the center of the pipe, at the very center, where you're the furthest away from the edges, the velocity will be the highest. And what we know about the flow conditions is that when it's laminar flow, meaning that when the Reynolds number is less than 2,000, then the velocity profile will be more parabolic in shape, whereas when we have turbulent conditions, meaning that the Reynolds number is above 4,000, then there is more of a flat velocity profile. There's not as distinct an increase of the velocity at the center of the pipe. It's just once you get away from the edges, then there's some average velocity, and at any given point, the velocity may momentarily be higher or lower than that average, but the main idea is that there is a flat profile that follows a logarithmic function when we have fully turbulent flow. But at both of the pipe walls, there's resistance being applied, and there may be, even in turbulent flow, like if most of this pipe has turbulent flow, if you get close enough to the edge of the pipe, there will be a small boundary where the velocity is moving slow enough that conditions are laminar right next to the edge. Just like in a fast-moving river, if out in the middle of the river the water's moving really fast, if you get pretty close to the banks, it's not moving as fast. And right next to the boundary between the bank soil and the water itself, the water has zero velocity. And so the same thing is true inside of a pipe, that there's this boundary layer where at the surface of the pipe, the velocity is zero, but then the further away you get from the surface of the pipe, the velocity is increasing. So this figure is just illustrating a velocity profile, and there would be some section of the flow field where the conditions are laminar because the velocity is slow enough in the vicinity of that pipe wall. The no-slip condition says that because materials like concrete or steel or cast iron exert a shear stress on the water, that the water can't flow with some positive velocity right at that boundary. That because of the shear stress that's being applied, there's some, however small, thin boundary layer that has zero velocity. And the further away you get from the surface, the the shear stress is decreasing, so the velocity increases. And if you change the flow rate, if you briefly increase the flow rate, that would bring the boundary layer closer to the pipe. Like if the bulk flow increases, then the boundary layer distance would get smaller. Or if you close a valve and reduce the flow rate, then the boundary layer gets thicker. And very quickly, the equilibrium will be reestablished where there's a balance between the shear stress that's being applied and a certain region which has laminar flow conditions. So how thick the boundary layer depends on what the fluid is. For instance, the temperature of the fluid can affect the viscosity. The fluid itself, oil has a different viscosity than water, which has a different viscosity from alcohol. And so the thickness of the boundary layer depends on the fluid characteristics, and also it depends on the characteristics of the surface. Because if you have a very smooth, polished pipe surface, then the boundary layer isn't going to extend very far from that. But a more rough surface could induce a much thicker boundary layer in the fluid field. So this figure, which comes from our text, depicts the thickness of the boundary layer. So here is some boundary layer where the shear stress is really high. So this black line is the shear stress, and the further you get from the edge of the pipe, the shear stress is decreasing. So remember, maybe at the center of the pipe, there is very minimal or maybe no shear stress that's being applied. But if you get right up next to the pipe wall edge, there's a high shear stress and therefore a low flow velocity. And so if you have a low flow velocity, then you may have a thin boundary where conditions are laminar. The boundary layer is sometimes called a laminar sublayer, and how thick it is depends on the degree of turbulence, the roughness of the boundary, and if you have water moving at a really high velocity through a pipe, then there's a large shear stress that's applied, but the boundary layer is small because most of the flow is going turbulent, and conversely, if you have a low flow velocity, the boundary layer is thicker. Another way to look at it is at the equivalent sand roughness of some different materials. We've got it here both in terms of millimeters and feet, and I mentioned this in the last class, but what it effectively is it's saying, what if we glued a bunch of sand grains to a pipe? What would need to be the average diameter of those sand grains to exert a similar amount of resistance as whatever this material is? So you can see, for example, if you've got a rough concrete, the rough concrete exerts as much resistance to flowing water as a surface would that had sand grains that were 3 millimeters in diameter. But if you've got a wrought iron pipe, that's much smoother, and so you'd need to have really small grain sizes, 0.045 millimeter diameter sand grain sizes, to exert a similar amount of resistance. This was just an attempt to kind of standardize the units that are used for comparing the roughness effect of different pipe materials. And it's kind of weird to think that there actually were, in the past, pipes that were made out of wood. In the same way that they use barrels for aging wine or bourbon or something, they used to have pipes that were made out of wood. I don't think that you're likely to encounter any of those, but there are occasionally still brick sewer pipes that are in use in certain places, or vitrified clay sewer pipes, but probably not in delivering potable drinking water, not a wood pipe. If we want to try and take a stab at quantifying the thickness of how deep into the water that boundary layer extends from the pipe, Morris and Wiggert tried that using shear velocity. So they attempted to relate the kinematic viscosity of a fluid and the shear velocity that is being experienced by a fluid to estimate how thick the boundary layer is. And so this is just a representation, a little sketch I made, which is showing a pipe which isn't actually smooth. If we microscopically zoom in on the pipe material, we'd see these little ridges. They look like little mountains sticking into the water if we zoom in close enough. And then the laminar zone is how thick the water is still Reynolds number 2000 or less. Now, what Morris and Wiggert suggested was that if the boundary layer is more than 1.7 times the equivalent sand roughness of the material, then it's considered a hydraulically smooth surface because the laminar sublayer is so much thicker than the height of those roughness elements that they don't project out into the turbulent flow. And so there's a different effect on the flow if these little mountains are completely contained within the laminar sublayer, then there's a different effect than if these little mountains, and of course you know they're not actually mountains, it's just these are the roughness elements extending into the flow field. But if the laminar sublayer is so small that it's less than 0.08 times the roughness, then they call that hydraulically rough. So there's a big middle zone there. You know, there's just in the same way that Reynolds number has below 2000 is laminar, above 4000 is turbulent, and transition flow is in between 2000 to 4000. Here, there is also a transition zone of where it's not necessarily hydraulically smooth and it's not hydraulically rough, but there are at least endpoints for where we could say firmly that the laminar sublayer is either dominating or the roughness elements dominate the effect of energy loss in the pipe. So there is a question in the homework assignment where I ask you to apply the Morris and Wiggert criteria. And there what you'll do is you'll look at what is the pipe made out of and find its equivalent sand roughness, epsilon, and then you'll compare that to the boundary layer thickness that you calculate, and then you'll say whether it's hydraulically smooth or hydraulically rough. Any questions about boundary layers or how to estimate their thickness? Okay, so we've got water flowing from this tank, and we want to try and determine what is the, let's see, we know the flow rate going through here, and we know the pressure that's required at the ground floor of the building, 350 kilopascals. The pipe is 250 meters long, it has a 250 millimeter diameter, and in this problem we're given the friction losses just outright, 16.4 meters. So what we're going to go through is the process of applying the energy equation to find out how high the water level needs to be in the tank. So that should sound familiar based on the fact that we talked a little bit about the related homework assignment problem on Wednesday, that you've got one similar to this for the homework assignment. We're going to do an example that illustrates how to determine the friction factor that should apply here. And we won't actually be applying the Moody diagram for that because the problem statement gives us the H sub F. So we're going to be estimating the friction factor as the only unknown in this Darcy-Weisbach equation. So F will be the only unknown there. And so then once we know the friction factor, then we'll be able to, from that, estimate what is the shear stress and the shear velocity, and then finally the thickness of the boundary layer. All right, so just to get things started, let's put the energy equation on the whiteboard here. We'll do some of this together, and then part of it I'm going to pause and allow you to do the calculations on your own without my interjection. But let's get some of the preliminary stuff out of the way. First of all, the flow rate is said to be 12,000 liters per minute. So we want that in cubic meters per second. So we have to divide by 60 to get liters per second. And then remember, there's 1,000 liters in a cubic meter. So if we do that, it's 0.2 cubic meters per second by dividing by 60 and then dividing by 1,000. Our hydraulic radius, this is a pipe that's flowing full. So the hydraulic radius, we can estimate just the diameter divided by 4, if you remember that simplification for a circular pipe that's flowing full. So the diameter is 0.250 meters divided by 4. So the hydraulic radius is 0.062 meters. Okay? And then the flow velocity, what's the velocity of the water that's going through the pipe? That's the flow rate divided by the cross-sectional area. So for a diameter of 0.25 meters, then the area is pi d squared divided by 4. So pi times 0.25 meters squared divided by 4. The cross-sectional area of this pipe is 0.04909 square meters. Okay, so that's what I'm going to use here for the velocity. So it's first of all the flow rate of 0.2 cubic meters per second divided by the area of 0.04909 meters squared. So the water's flowing at 4.074 meters per second. That's pretty fast. Yeah, do you have a question?
I guess the velocity is 4.07.
Good.
Oh.
Yep. Good. So the head loss, H sub F, the head loss due to pipe friction is 16.4 meters. Now here it said neglect local losses. Do you know what I mean by that? What are local losses?
Aren't they due to like different fittings in the pipes and things like that?
That's right. So it's the local losses are energy loss that's due to water going through like a valve or maybe a bend. You know, for example, when the water's coming down from this tank and then it bends because it's now going through the pipeline, there'd be a little bit of energy loss due to just a change in direction. Sometimes local losses are called minor losses because compared to pipe friction, they're relatively small in magnitude. So if we're really trying to be super precise, we include local losses, but in just an illustration example like this, we'll just assume that all of the energy that's lost is because of pipe friction. So I just wanted to mention that's what we meant about the local losses here. Okay, so H sub F is 16.4 meters. So let's think about the energy equation. The pressure head, the elevation head, the velocity head. Now there's no pump, so I'm not even going to write the pump head term. Is equal to the pressure head at 2, the elevation at 2, the velocity head at 2, and then the head loss due to pipe friction. Here, H sub L, that means H sub L is H sub F, head loss due to pipe friction, plus also the local losses. So in this problem statement, it said, let's neglect the local losses. And so the head loss is only due to pipe friction in this example. So I'm just going to write here as our final term, H sub F, the head loss due to pipe friction. Okay, so the water, when it starts, is in this elevated tank. So I'm going to use location 1 is the top of that elevated tank where the water is in contact with, do you remember what the triangle means?
Atmospheric pressure.
Atmospheric pressure. So here at location 1, where the cursor is right now, the pressure is 0. So the pressure head term can be canceled out. And also the water in that tank is stationary. So the velocity head term can cancel out at 1. So the only unknown on the left-hand side of the equation is Z1. And we know at location 2 is the base of the building, the office building's ground floor. So that's location 2, and we know some things about that as well. We know that the pressure at 2 should be 350,000 newtons per meter squared. That's P2. What's gamma? What value should I use for gamma, since we're in SI units?
98.
Good. 9810 newtons per meter cubed. Okay, so that's the pressure head term. Z2, it looks like, is 20 meters. So plus 20 meters. The velocity head term, the water velocity, as the water is about to go into the building, it's in the pipe and moving at 4.07 meters per second. So 4.074 meters per second, and we'll square the velocity divided by 2g plus the head loss due to pipe friction, which is 16.4 meters. Okay, so we've substituted some numbers into the energy equation. This semester, you'll never see me write numbers on the whiteboard unless there's units accompanying them. And I'd encourage you to follow that example, because you're going to catch mistakes. If you also write the units down, then it's just much easier to catch a mistake. For example, what if I just written 350? Because it's 350 kilopascals, so why not just write 350? Well, if I always force myself to write the units, I'd write 350, and then I'd look at the units and I'd say, oh, right. Since I'm dividing by newtons per meter cubed, I actually need it to be 350,000 newtons per meter squared. So I think if you always get in the habit of including the units when you do numerical substitutions into a formula, it'll take just a moment longer as you write it on the page, but it'll pay big dividends in capturing mistakes where the units weren't going to work out. Okay, so if I just look at what is the magnitude of each of these terms, this pressure head is 35.678 meters of pressure head. The elevation obviously is 20 meters. The velocity head is 0.846 meters. So what is Z1? Can you calculate that? I've got a number in mind. I want to see if you've got the same number in mind for Z1. And meanwhile, I'll bring that up on the screen just to get it recorded into the lecture video as well. Anybody get 72.9 meters is how high the water has to be? So we need to have the water high enough. You know, water elevated is providing energy to the system. So why do we need a certain amount of energy? We need 35 meters of elevation to provide the 350 kilopascals. So that's how much of the elevation is set aside for pressurizing the water. 20 meters of elevation in that tank on the left, simply because the building on the right has 20 meters of elevation. So that's a part of it. The velocity head, certain amount of energy has to be used to accelerate the water from motionless inside of the tank to flowing through the pipe. And then 16.4 meters is how much energy has to be provided to overcome pipe friction. So in total, we know the required water elevation inside that tank on the left, 72.9 meters. All right, so that takes us through just part A. Now, what is the Darcy-Weisbach friction factor? Well, we know H sub F. We know the length of the pipe, the diameter, the velocity. So we can calculate the Darcy-Weisbach friction factor equivalent just by rearranging the formula. Let me write that on the whiteboard. If we just rearrange things algebraically, okay, so it should be F is H sub F times the diameter times 2g divided by length times velocity squared. Okay, so 16.4 meters times 0.25 meters is the diameter, 2 times g, 9.81 meters per second squared, divided by the length of the pipe here, 250-foot run from the tank to the building, and then the velocity squared, 4.074 meters per second squared. So if you put that in and solve for F, I think what you'll get is 0.0194. Okay, so we've got the friction factor, and now that we have that, we could estimate what is the shear stress. So the shear stress, we're going to have to know what is the slope of the energy grade line. So S sub F is defined as H sub F, the energy loss due to pipe friction, divided by the length of the pipe. So here, this formula, we know that the slope of the energy grade line is 16.4 meters of energy loss divided by 250 meters of pipe length. So the slope of the energy grade line then is 0.0656. And then substituting that slope of the energy grade line into the formula for shear stress allows us to estimate that the shear stress is 40.2 newtons per meter squared. Let me zoom in a little bit more just to make that easier to read. Okay, so shear stress has the unit weight of the liquid, a hydraulic radius, and of course this is a circular pipe where the water's flowing full, so it's just the diameter divided by 4 for the hydraulic radius, and then we use the slope of the energy grade line, which we just estimated. So 40.2 newtons of force are being applied to the water for every square meter of area that the water is in contact with the pipe surface. That's the amount of shear stress that's being applied. And then what about shear velocity? So you can see here's our formula for shear velocity, where it's the shear stress divided by density. And look, I almost made a mistake. See how I had written 9810? But then I remembered, oh, wait, density, not unit weight. So the density of water is 1,000 kilograms per cubic meter. So the shear velocity is 0.2 meters per second. Okay, so then how thick is the boundary layer? If we know the shear velocity and then the kinematic viscosity of water is at just standard temperatures, kinematic viscosity of water is 1 times 10 to the minus 6 meters squared per second. So I'd like you to calculate how thick is the boundary layer with this kinematic viscosity and the shear velocity, which we just calculated is 0.2 meters per second. How thick is the boundary layer according to Morris and Wigert criteria? All right, so what we should get is if we apply that shear velocity of 0.2 meters per second, then the boundary layer thickness is 5.8 times 10 to the minus fifth meters. So that's 0.058 millimeters. So that's how thick the boundary layer is. There was one more part of this question. I was suggesting that what we could do is we could back calculate what is the Reynolds number and use the Moody diagram to try and find out what is the epsilon, and from the epsilon identify what is the pipe material. But we're almost out of time, so I mean this last part D was maybe just goofing around really. So we'll leave it at calculating the thickness of the Morse and Wigert criteria. We've got 1 minute left. I just wanted to remind you that we've got this homework due on Wednesday. I can stick around for a few minutes after class if you have any questions. And of course, I'll be answering emails over the weekend if anything comes up, or stop by my office. I'll be happy to help you out. So I'll see you for class on Wednesday. We don't have class on Monday.
Can you pull up the answer again real quick?
Yeah.